add the EMF induced by moving charges into our system. So even in a non-changing magnetic field, we can get an electromotive force if we have a wire that's moving in a stationary constant magnetic field. So you remember the Lorentz force from chapter 8. It combines the electric force, QE, we'll learn about on day 1. That's the force at a right angle to a moving charge. Okay, and so we can talk about this as having electric and magnetic parts. If there's no electric field, okay, we've still got this magnetic part, maybe if there's a static magnetic field around. And so we can talk about an electric field due to motion. It's a force caused by the magnetic field divided by the charge. So U cross B over Q. U cross B. U cross B over Q. Okay, big deal. But this is going to connect up to our quantity about how we have different ways for the magnetic flux to change. So when we're talking about the electromotive force, it's a rate of change of magnetic flux, B dot ds, which we could get a non-zero answer here if B is changing with time, or if the size of the surface is changing. And one really classic example is the dot product. Okay, we got to think about that, of a static magnetic field from a magnet in a motor dotted with the surface area of a coil. That dot product is 0 when the magnetic field and coil are aligned, and 1 when the magnetic field is going up through the coil. Okay, so that you can get, even with a static magnetic field, a time-changing magnetic flux if something's rotating or a loop is changing size. So we had to think about that as a source of EMF. So we can move this ddt in here only if the limits of integration aren't changing. dB dt dot ds from time-changing field. Okay, plus this other part. Okay, we're going to do, well, V is E dot dl. We're going to, Vm is going to be EM, emotion, dot dl. This other piece comes along like this. And we might as well substitute this in. U cross B dot dl. Motion of a conductor or something that's carrying these charges in the presence of a magnetic field. Okay, and so to figure out the induced current in a system that could have both things going on, and one example, let's add to the sliding bar example. We've got a metal slider that can contact this thing, and it's moving with a velocity u, and it's in a magnetic field And that whole thing, that magnetic field, could be coming from a coil. It's going perpendicular to the page. It can be changing with time. Sine omega t, some initial amplitude in the z direction. And then we have this moving, and we can account for both parts of it. We split out the EMF into time varying field and motional EMF.